Hi everyone. So today we're going to be talking about unit step functions and the second shifting theorem. And what I mean by that is we've already talked about what happens when we shift in the frequency domain, and that corresponds to multiplication by an exponential in the time domain. What we're going to look at now is what happens when we have a shift in the time domain. How does that come out in the Laplace domain? So I'm going to start by reminding you exactly what the first shifting theorem says. So the first shifting theorem says that if you are looking at the Laplace transform of e to the at times f of t, then when you pull that over into the Laplace domain, multiplication by the exponential e to the at takes the Laplace transform of f and it shifts it to the right by a units. And likewise, the inverse Laplace transform of f, capital F of s minus a, is equal to e to the at f of s minus a. And this is called the first shifting theorem. Now, if we want to talk about translations in the time domain, so what about f of t minus a? What happens if I shift in the time domain? Well, in that case, we're going to have to introduce a new function that we haven't talked about yet, but one of the most useful functions in modeling, called the unit step function. So let's start by talking about the unit step. So the unit step function is defined as uat is equal to 0 if t is less than or equal to a. And typically, because we're working in the Laplace domains here, we're going to force t to be 0 or bigger. And then once we hit the point a, then the switch turns on and the function becomes 1 for the rest of time. So in graph form, that looks like this. If this is the point a, you have a function that starts at 0. It travels along until it gets to a, and then it leaps up to 1, and it stays 1 forever. Now, the thing about unit step functions is they can be used to turn functions on and off. And this is going to be the basis for taking piecewise defined functions and turning them in to functions that just have a single definition. So let's look at a quick example so we can see exactly what it is the unit step function does to another function. Let's look at the function f of t is equal to u2 of t times t squared. So that function is going to be 0 from 0 to t equals 2, because this function is 0 from 0 to t equals 2. So it automatically is going to force cases into the definition of this function, where now this function is going to be equal to 0 if t is between 0 and 2, and 1 times t squared if t is bigger than 2. And so if you plot that, what you get is this. Sort of a ghost parabola for the beginning here. And then all of a sudden at t equals 2, the parabola actually turns on. So this function looks like this. It's 0 for a while until it gets to t equals 2. And then it leaps up and starts being the parabola past that point. Okay? So you can think about it as a switch. The unit step function is a switch. When it turns on, it activates a function. And when it turns off, it deactivates a function. What that means is we can use it to define other functions as well. So for example, suppose that you start with a function that implicitly has a piecewise definition. I don't know. So a function we've used in this class a couple of times is f of x is equal to some sort of shifted absolute value. So let's look at 1 minus the absolute value of x minus 1. So that function is an absolute value that's been turned upside down, shifted to the right by 1, and then pushed up by 1. So it looks like this. Let's suppose that because we're working in the Laplace domain, we're going to let x be greater than or equal to 0. If I plotted this, I would get this. So this function is equal to a function that looks like this. So it goes up, and then it goes back down again forever like that. And that change happens at t is equal to 1. So this is what that sort of shifted, flipped around absolute value looks like. If you trace through the definition, it's pretty easy to see that this function is equal to the function x on this branch. And on the other branch, it's equal to 2 minus x. That just has to do with evaluating the absolute value on the different pieces between 0 and 1 and between 1 and infinity. So if I want to write this down as one definition, instead of having to write down f of x is equal to x when x is between 0 and 1, and 2 minus x when x is bigger than 1. If I want to take that and I want to write it down in one piece, I can use unit step functions to do it. So the unit step function of the first part, how would I turn on the function x and then turn it off when I got to 0? So I start with the function x. And now I need to turn that function off as soon as I get to x is equal to 1. To do so, I'm going to multiply x by a unit step function that starts at 1. So what I can do is I could subtract x times u1 of x. Because what will that do? That function will be x between 0 and 1. Because the unit step function is not active there. It's not on. But as soon as I get to x equals 1, this turns on and then makes that thing into x minus x, which basically cancels the x out. Another way of thinking about this is x times 1 minus u1 of x. That is, we start with the function on, and as soon as we get to x is equal to 1, we flip a switch which subtracts that function from itself and turns it off. The next part of the function is off until we get to x is equal to 1. So we're going to take that and we're going to add it to, well, 2 minus x, because that's the second part of the function, but I need it to turn on when we get to x is equal to 1. So what I can do is I can multiply it by u1 of x. And now what will that do? Well, u1 of x is 0 until we get to x is equal to 1, which means this is off between 0 and 1. And as soon as we get to x is equal to 1, u1 of x turns into a 1, which turns that function on. So the upshot of this is f of x. These two definitions, this definition and this definition, are the same function. But now I've got that function without absolute values in it, and it's not broken up into cases like it is here. So I could just treat it as a single formula that I could use in a differential equation or to do calculus with. So unit step functions are a way of representing piecewise functions, which is an incredibly important thing to be able to do. So let's do another example for practice. Suppose I have this function. F of x is equal to 2 when we are between, say, x values of 0 and 1. Maybe it's equal to x squared when x is between 1 and 2. And then maybe after x squared, the function turns into the cosine of x. So that's a piecewise function with 3 parts. If you want to plot it, it's going to be equal to the constant 2 for a little bit, and then it changes and turns into x squared between 1 and 2. And then after that, it's a cosine. Okay, 3 pieces, 3 distinct areas where the function has different behavior, like any piecewise function. How can I take that and translate it into a single equation using step functions? Well, the first thing I'll do is I will build the switches that turn these different pieces of the function on and off. 2 is on from x equals 0 until we get to x is equal to 1, and then it turns off. So I'm going to say 2 times, well, I could say 1 if I wanted to, or I could write u0 of x, which is basically the same thing because u0 of x is a switch that is always on. So u0 of x is when that function turns on, and I can subtract off u1 of x because that's the switch that turns it back off again. Plus x squared times u1 of x because that's where the parabola turns on. And then I have to subtract off the switch that turns it back off, which is u2 of x. And the final piece of the function is cosine of x. And that I can just turn on, then never turn off because it's on forever past that point. So I could write u2 of x. And so this function is the single line version of this piecewise defined function up here. Okay? So these are the same function, but the unit step function is a way of representing it as a single line. You might think, why is that important? It's great that we have a way of encoding a split case function as a single line, but how could I use that? After all, this is a function that is discontinuous, and it's not just discontinuous. It's also got this terrible, it has no derivative behavior, right? So the answer is that in a lot of cases in modeling problems, you have forcing functions that are defined piecewise. Let's suppose that you write down a differential equation for a generic mass spring system, which is usually written in the form x prime prime plus ax prime plus bx is equal to 0, where really there's like k, the spring constant is in here, and the damping constant is in here, and the mass is in here. We'll just abstract that away for a moment, and we'll just look at this version of it. So as long as a and b are non-negative, this represents a mass spring system. And it's typical in a mass spring system to put a function here, which is a forcing function. So with a forcing function, it looks like x prime prime plus ax prime plus bx is equal to some function f of t, where this thing is the forcing function. And a lot of times you want that forcing function to be piecewise defined. You want the conditions of the system to be able to change with the flip of a switch, and to study what happens to the system when that switch flips. So if you want f of t to be piecewise, you're going to have to deal with either lots of integrals, because every case is going to correspond to a different differential equation, or if only there was a way that I could turn f of t into a single equation, and then maybe if we hope hard enough, there'll be a Laplace transform that will help us incorporate all of that into the method that we've been developing. And of course, that's going to be what turns out to be the case, that unit step functions actually do have a Laplace transform. And so the big deal of all of this is that this is a way of introducing piecewise functions, piecewise forcing functions, and adding it to all of the ideas we've been doing with the Laplace transform. And that's going to be the content of the second shifting theorem, which we will write down right now. So the second shifting theorem says the following. Let's write down that the Laplace transform of little f is equal to capital F of s. So let's let this be the case. Just our usual notation for the Laplace transform. Then the Laplace transform of a unit step function times a time domain shift of a function is equal to multiplication by an exponential in the frequency domain. So we still have the correspondence between shifting and multiplication by an exponential, but now we have to do not just a shift of the function, but a shift of the domain of the function as well. So the UA of t is basically saying f is shifted, but we have to presume that f doesn't start until the point t is equal to a. So you can interpret this as saying this gives you a new starting spot for f. This shifts the domain of f, and this says that f starts at a. So this shifts f, and f starts at a. Okay? And that, just like in the first shifting theorem, that shift corresponds to a multiplication by an exponential, but with the reverse sign. In the case of the first shifting theorem, we had that a shift corresponded to an e to the at for t minus a. Now we have a shift in the opposite direction. So e to the minus as f of s. Okay? Of course, every Laplace transform theorem comes with an inverse Laplace transform theorem. So the inverse Laplace version of this says that L inverse of e to the minus as capital F of s is equal to ua of t f of t minus a. And we'll go through some examples of how to actually do this. There's another formula that gets used here, which is convenient, which is if you're computing a Laplace transform and you don't want to have to push f so that f has a shift in it as well as the unit step function, there's a way of just doing it directly. So what I mean by that is if you had something like the Laplace transform of a unit step function so that the function turns on at t equals a, but then it's just multiplied by an f of t, so f doesn't have that shift built in, then you can compute that by writing down e to the minus as, just like typical, right? That the unit step turns into that e to the minus as, but then you take the Laplace transform of the shift of f. So it just incorporates that shift that should be there, because in the first version of the second shifting theorem, the a here has to correspond to the shift here. Let's find the Laplace transform of some piecewise functions. So let's find the Laplace transform of f of t, where f of t is equal to 0 between t equals 0 and t equals 1, t minus 1 when t is between 1 and 2, and 1 when t is bigger than or equal to 2. So this is a function that looks like this. It travels from 0 to 1, and it's 0. When it hits to 1, it turns into the function t minus 1, which pops it up like this until you get to t equals 2. And then it just stays at height 1 forever after that. So it's sort of a ramping function. It ramps up to a certain level and then just stays on. This sort of function shows up a lot in physical applications. All right. So how am I going to compute this Laplace transform? The first thing I need to do is I need to take this piecewise function and write it down as a single formula. So quickly, this formula looks like f of t is equal to t minus 1 times u1 of t minus u2 of t plus 1 times u2 of t, where those switches are turning the function on and off. So the function is 0 between 0 and 1, because everything is 0. All of these switches are 0 between 0 and 1. Then, when you get to t equals 1, what turns on? Well, this turns on. Everything else is still 0 because u2 of t is still 0, but u1 turns on, and that turns the function into t minus 1. Then when you get to t equals 2, what turns on? This and this function turn on. And when they turn on, that turns off the t minus 1 and turns on the 1 that produces the function for the rest of time. So this is this function up here. Now, it's convenient to algebraically rewrite this, and so we'll do so. If you rewrite this formula, I think you get t minus 1 times u1 of t minus t minus 2 times u2 of t. That's just multiplying out, rearranging, factoring, you get this. Okay, algebra. Now we can take a Laplace transform, because both of these functions fit into the form of the second shifting theorem. So the Laplace transform of f is equal to the Laplace transform of t minus 1 u1 of t minus the Laplace transform of t minus 2 u2 of t. And both of those functions fit the form of the second shifting theorem. All right, so from here, let's take this line and see if we can actually compute these Laplace transforms. So let's start with the Laplace transform of t minus 1 times u1 of t. What does the theorem say that we're supposed to do? So the theorem says that the Laplace transform of ua of t, f of t minus a, is supposed to be equal to e to the minus as times f of s. So we need to know what the f is in this case, right? I need to know what f is. Well, f is supposed to incorporate the shift. And so it's going to be the case here that for our problem, little f of t is just the function t, because then f of t minus 1 is the function t minus 1. In fact, f of t is equal to t is a function that will work for the whole expression, but I'm breaking this up into pieces just so we can see how to operate piece by piece. So this is enough information for us to do this step. The Laplace transform of t minus 1 times u1 of t when f of t is equal to t should be, all right, so we get e to the minus 1s times the Laplace transform of f of t. That's what capital F of s means. Capital F of s is the Laplace transform of f of t. But the Laplace transform of f of t is the Laplace transform of t, which is 1 over s squared. And so we get e to the minus 1s times 1 over s squared. Likewise, if we do the Laplace transform of t minus 2 times u2 of t, we're going to get an exponential piece corresponding to the shift, and that's going to be e to the minus 2s. And then the Laplace transform of the function little f. But little f in this case is also the function f of t is equal to t, because this function is t with t minus 2 plugged in. So we're going to get the Laplace transform of t again, so we get 1 over s squared again. So what do we have? We have that the Laplace transform of the combined function, which is just the sum of the two pieces, is equal to the Laplace transform, that the Laplace transform of f is equal to e to the minus s times 1 over s squared plus e to the minus 2s times 1 over s squared. And this is typical of the way these problems work with piecewise functions. You have a piece of the Laplace transform that corresponds to each piece of the original function. And those pieces control sort of what's happening in the Laplace domain, one piece contributing for each piece of the original function. So let's do another example. How about the inverse Laplace transform of 2e to the minus s over s squared plus 4? What function did that come from? Well, I have this e to the minus s here, and that means I know that this must have come from a shift in the time domain. So I identify this exponential right here. This corresponds to a time domain shift. So what is the time domain shift? What's the a here? Remember that it's e to the minus as, and so a is equal to 1 in this case. Okay? So when we're computing an inverse Laplace transform, it's typical to store the things that we're going to do in some sort of notation as we go. So let's rewrite this slightly. This is the inverse Laplace transform of e to the minus s times 2 over s squared plus 4. And I know what the inverse Laplace transform of 2 over s squared plus 4 is. It's the sine of 2t. So how am I going to record the action of this e to the minus s? One way to do that is to write down that you're going to have a u to the 1t, and then you're going to have an inverse Laplace transform of 2 to the s squared plus 4, but then you have to remember that you're going to shift the variable in the end, that the t that you're going to get is going to be replaced with t minus 1, so that you get the shift in the function as well. So this is the basic way that you untangle the effect of this exponential in the Laplace domain. It turns into a step function, but it also shifts the function as well. And so the final step here is to write this as u1 of t times the sine of 2 times t minus 1. And that's the best you can do in this case. I mean, you could, if you wanted to, you could multiply this out and get 2t, sine of 2t minus 2. But this is a sort of standard way of writing this. The big deal is that when you're computing these shifting theorem problems in the inverse direction, that those exponential functions turn into step functions, which turn the function on at the beginning of the shift. And then you have to also shift the function so that it gets to the point where it's supposed to start. Okay? This is easier with practice, I promise. So what's the big application of unit step functions? Well, They show up all the time in the solution of differential equations. So let's look at a simple differential equation that has a piecewise forcing function. So we're going to impose a force, and then we're going to change the force that's being imposed at a certain point. So let's look at y prime minus y is equal to f of t, where f of t starts out as 1 as long as we're between 0 and 1, and then it turns into the function 1 minus t whenever t is bigger than 1. And I guess I need initial conditions as well. So let's impose the condition that y of 0 is equal to 0. So solve the differential equation. Now, in the earlier methods you've used for this, you would actually have to split this differential equation into two separate differential equations. One that corresponded to y prime minus y is equal to 1, and a second equation that corresponded to y prime minus y is equal to 1 minus t. And you'd have to solve those separately. You'd have two different solutions that you'd have to say this is active in this spot and this is active in this spot, and it's kind of a mess because there's all these cases to track. With the Laplace transform and the unit step functions, we're going to be able to write down a single answer to this equation, which is very useful. So the first thing we're going to do is translate f into a single function using unit steps. So we write down y prime minus y is equal to, okay, well the function is just 1 for a while, and then it's 1 from 0. Again, u of 0 and 1 are the same function, but it's consistent to always be using unit steps to turn things on and off. So 1 times u0 minus u1 of t. Why u1 of t? Because that's when that part of the function turns itself off. Then what's going to happen is it's going to turn into 1 minus t from u1 of t and onward. That switch turns on when t is equal to 1 and keeps the function 1 minus t for all time. It's pretty typical to rewrite this as 1 minus u1 of t plus 1 minus t u1 of t. And then I can do some algebra here and rewrite this function as y prime minus y is equal to 1 minus t minus 1 u1 of t. So just rearranging. And this thing I can take a Laplace transform of. So I'm going to take that function right there, and I'm going to use the Laplace transform to solve it. Y prime minus y is equal to 1 minus t minus 1 times u1 of t, and y of 0 is equal to 0. This is the same equation that we started with. All right, so hit it with a Laplace transform. And what are we going to get? So I'll L this side, and I'll L this side, and I get s times capital Y of s minus y of 0. That's what y prime turns into, minus capital Y of s is equal to the Laplace transform of 1, which is 1 over s, minus the Laplace transform of t minus 1 times u1 of t. Well, we saw that in an earlier problem. What that's going to do is we're going to get s, y of s. Y of 0 was 0, so that disappears. Minus capital Y of s is equal to 1 over s. And then the Laplace transform of this is going to be e to the minus s times 1 over s squared. Because the function little f here, f of t, was just equal to the function t with a t minus 1 plugged in. It's just that we're going to have this exponential running around. You should think about the exponential as storing the fact that in the time domain, something changed at t is equal to 1. That it went from one behavior to another behavior there. So if we just do the algebra, s minus 1 times capital Y of s is equal to 1 over s minus e to the minus s times 1 over s squared, so that capital Y of s is equal to 1 over s times s minus 1 minus e to the minus s times 1 over s squared times s minus 1. Now you got to do partial fractions, right? So this is pretty typical. This right here, this is the Laplace domain function that represents the entire original system. So we've solved it. This equation is now solved in the Laplace domain. What we need to do is we need to take that and translate it back to the time domain, which is going to require using the inverse Laplace transform. And to do that, we're going to need to do partial fractions. So after you perform the partial fraction step on this problem, you're going to get the following. You're going to get that y of s is equal to minus 1 over s plus 1 over s minus 1. That's an easy partial fraction. And then you're also going to get this e to the minus s floating around, and it's going to be multiplied by this pile of things. 1 over s minus 1, minus 1 over s, minus 1 over s squared. After you split up this, it breaks into 3 pieces because there's a repeated power of s, which is why you get the s and the s squared, and then the s minus 1 also gets a term. So you can solve that using your favorite method for partial fractions. When you do that, now you've got things that you can translate backwards, because everything here is easy. It's easy to go backwards with the second shifting theorem. So you can just walk down the line. If this is capital Y, then little y of t has got to be equal to, well, the inverse Laplace transform of 1 over s is 1. So we get a minus 1. The inverse Laplace transform of 1 over s minus 1 is e to the t. Now, what we're going to do with the rest of these is we're going to have a unit step function that corresponds to this. And then we're going to have to shift the inverse Laplace transforms of all of these. The unit step function that corresponds to e to the minus s is u1. And then what happens to the stuff inside? 1 over s minus 1 came from e to the t. But that t has to be shifted because remember that the e to the s turns into both the step function and a shift of, so it turned into the step function, and it also turns into a shift of t turns into t minus 1. So the Laplace transforms of the functions are easy. E to the t and 1 and t, but all of those t values have to be shifted to t minus 1 because that's what that exponential in the Laplace domain records. And so for the last step, we get y of t is equal to minus 1 plus e to the t minus u1 of t times the shifted version of all these things, e to the t minus 1 minus 1 minus t minus 1. And so that is the solution to the differential equation. And that's nice. We don't have lots of cases. We solved it all in one go. We didn't have to break things up into different pieces depending on which part of the forcing function we were on. We have a single function description of the solution to the differential equation. And this is the point of working with unit step functions, is that it allows us to deal with piecewise forcing functions in a very straightforward and comprehensive way, where everything's kind of all in one piece. All right, so this is stuff that needs to be practiced to be learned. We have 2 more ideas left to go, and we're done with the course.